and welcome everyone to the presentation of NATSA, exploiting near data processing to accelerate time series analysis. Let's start with the executive summary. The problem is that time series analysis is bottlenecked by data movement in conventional hardware platforms. And the goal of this work is to enable high performance and energy efficient time series analysis for a wide range of applications. As contributions, we propose the first near data processing accelerator for time series analysis, which is based on matrix profile algorithm. NATSA evaluations show that it provides up to 14.2 times higher performance and consumes up to 27.2 times less energy than a DDR4 platform with 8 out of order cores. And also, it outperforms an HBM NDP platform with 64 in order cores by 6.3 times while consuming 10.2 times less energy. Here you can see the outline of the talk. So let's start with the motivation. Time series analysis has many applications like climate change, medicine, economics, signal processing, even astronomy, and many more. The two main primitives that we are interested in when performing time series analysis are motifs and discords. So given a sliced time series into subsequences, motif discovery focuses on finding similarities, while discord discovery focuses on finding anomalies. Let me show you a nice example of anomaly detection. Here we have a very regular time series in blue that has a very different subsequence over here. So if we use Euclidean distance to check what is the similarity between the different subsequences of this time series, we will obtain for those subsequences that are very similar to the rest ones, distances that are very close to zero, and for the subsequence that is very different to the rest one and its surrounding zone, we will obtain high distance values. So this is an example of a discord or an anomaly. The state-of-the-art tool to perform time series analysis is matrix profile. It is an algorithm and also an open source tool that is intended for those tasks, to detect motif and discords. It is very easy to use because only as a user, you only need to provide the subsequence length. And let me give you a very high-level overview of how this algorithm works. So let's assume that you have an input time series and you already define a subsequence length that is M. So what this algorithm does is to create a matrix that is the one that's shown over here. And basically each cell of this matrix contains the distance in the Euclidean, using the Euclidean distance with comparing a couple of subsequences that are indexed by the row and the column of the matrix. There is a problem, and if the time series is quite large, the size of this matrix could be huge. And so what the algorithms usually do is to avoid storing it in memory. And instead of that, they store what they call the profile and the index vectors. The profile and the profile vector basically stores the minimum value of each row of the matrix. This means that for every subsequence that we have in the time series, we store the minimum distance with respect to the other subsequences of the time series, or in other words, what is the closest neighbor to this given subsequence. In the index vector, what we store is the position of this neighbor with respect to the time series. If you want to know more details about the algorithm, please take a look to the paper. Nice. So SCRIMP is the state-of-the-art CPU matrix profile implementation, but there are also GPU and heterogeneous CPU and GPU available. And what we do in this work is to characterize SCRIMP using an Intel 7.5 KNL. To do so, we basically increase, we check the scalability of the algorithm by increasing the number of threads using two different memory technologies. And what we can see in this plot is that when we use a slower DDR4 memory, the performance of the algorithm doesn't scale beyond 32 threads. While if we move to a faster memory like the HBM1, we obtain higher speed. To further confirm this fact, we also build the roofline model of the algorithm. And as you can see here, SCRIMP is placed in the left part of this plot, which means that its arithmetic intensity is quite low. Based on that, we conclude that SCRIMP is heavily bottlenecked by data movement. So far, I show you that time series analysis has many applications, and it is bottlenecked in commodity systems by the memory. So the goal of this work is to enable high performance and energy efficient time series analysis for a wide range of applications by minimizing the overheads of data movement. And to this end, we propose NATSA, the first near data processing accelerator for time series analysis that exploits 3D stacked HBM memories and specialized processing logic. Let's take a look to NATSA design. From the high-level perspective, NATSA is designed to fully exploit the memory bandwidth of HBM and employ the required amount of computing resources to provide a balanced solution. NATSA consists of multiple processing units, or PUs. Each PU includes energy-efficient floating point units and bitwise operators, and they are designed to compute batches of diagonals of the distance matrix following a vectorized approach. Let's talk about NATSA integration in the system. In this figure, you can see how NATSA can be used in a system. So what we have is an HBM cube over here that is connected to NATSA using an 8-channel interface. NATSA, as I said, is composed of several processing units, and both components are placed in the same silicon interposer. Those PUs consist of 4 hardware components. First, we have a dot product unit. Second, we have a distance compute unit. Third, we have a dot product update unit that, using the dot product calculated from the dot product unit and adding a couple of terms, it reduces most of the computation. And finally, we have a profile update unit that updates the profile and index vectors if needed. Additionally, we provide 1 kilobyte scratchpad memory per PU to store temporal data. Next, let's take a look to how the execution flow happens in NATSA. This execution flow comprises several steps. The first one is to calculate the dot product computation of the first element of the diagonal. Then we calculate the Euclidean distance of the first element of the diagonal. Next, we perform the first profile update if needed. Then we update the dot product for the next iteration, and we continue with the second and successive Euclidean distance computations. Finally, we perform the updates if they are needed. One key design point in NATSA accelerator is to ensure load balancing among the different PUs, and to do so, we use a static partition scheduling. We basically assign pairs of diagonals to each PU that sum the same number of cells to compute. Let me show you a nice example of how this can be done. So in this case, we have a couple of PUs, PU0 and PU1, and what we do is to assign PU0 the third and the last diagonal, and to PU1 the fourth and the ninth diagonal. We continue assigning diagonals in this way until we reach the full matrix schedule across the DPUs, and if you sum the number of elements that each PU has to compute are the same. So this is what we are interested in. Next thing to take into consideration is to providing a programming interface to the user. So basically, the user is responsible for allocating the time series and also providing the subsequence length. Then NATSA will provide the user the computed profile and profile index vectors as a result. Here you can see how NATSA API looks like. That basically is comprised of a function that under the hood pre-calculates the statistics, like the standard deviations and means for every subsequence of the time series. It allocates the private profiles that are needed for all the PUs of NATSA. It calculates the scheduling, the static scheduling we just mentioned. It starts the accelerator, and finally, it performs a final reduction. Now, let's move to NATSA evaluation. As methodology, we use several simulation environments. First, we use an in-house integration of setsim and Ramurator to simulate the general purpose hardware platforms. And we use MacPad to obtain the area and power for the general purpose hardware platforms. Then we use the integration of Aladdin and Gen5 to obtain performance, power, and area of NATSA. And finally, we obtain the memory side power consumption using Micron Power Calculator. As hardware platforms, we define several representative simulated ones. we have DDR4 out of order, which basically comprises of 8 out of order cores. We have DDR4 in order, which includes 64 in order cores. We have HBN out of order with 8 out of order cores, HBN in order with 64 in order cores, and NATSA that is composed of 48 PUs. Additionally, we evaluate NATSA against real hardware platforms like an Intel 7500KNL, an NVIDIA Tesla K40C, and an NVIDIA GTX 1050. First, let's take a look to the performance of NATSA. To do so, we compare the performance of NATSA with respect to general purpose hardware platforms. And in this figure, we plot the speed up of NATSA for different time series lengths that are representative of most common applications. And as you can see, NATSA in green is the one that provides the better performance. Concretely, NATSA outperforms the baseline, which is DDR4 out of order, by up to 14.2 times, 9.9 times on average. If we take a look to the power consumption, we can compare the power consumption of NATSA with respect to the simulated and real hardware platforms. In this figure, you can see what are the power requirements in terms of watts of all the evaluated platforms. And as we can see here, NATSA is the one that requires the least amount of power. One thing that is worth to mention is that most of the NATSA's power is consumed by memory. Then we evaluate and compare the energy consumption of NATSA with respect to the simulated and real hardware platforms for a particular and given executor. In this case, instead of using watts, we measure energy in joules. And as you can see here, NATSA is also the one that provides the least amount of energy that is required. Concretely, NATSA reduces the energy consumption by up to 27.2 times over DDR4 out of order, by up to 10.2 times over HBN in order, and by up to 1.7 times over the NVIDIA Tesla K40C. Finally, we compare the area of NATSA with respect to the simulated and real hardware platforms. And as you can see here in this plot that is up to scale, NATSA is the one that requires the least amount of area. And it is worth to mention that NATSA is built using 45 nanometer technology node, and this is the platform that NATSA is using a bigger technology node than the other platforms. So even this fact, it is the one that requires the least area. So let's finish the presentation with the executive summary. The problem that this work tries to solve is that time series analysis is bottlenecked by data movement in conventional hardware platforms. The goal is to enable high performance and energy efficient time series analysis for a wide range of applications. And to this end, we propose the first near data processing accelerator for time series analysis based on the matrix profile algorithm. NATSA evaluations show that it provides up to 14.2 times higher performance and consumes up to 27.2 times less energy than a DDR4 platform with 8 out of order cores. And it also performs an HBN NDP platform with 64 in order cores by 6.3 times while consuming 10.2 times less energy. So that is all from my side. Thanks a lot for your attention, and I'll be happy to answer any questions you may have.
Thank you, Ivan. Very efficient. Are there any questions for Ivan? Okay, I'll have a question for you. So NATSA is very specialized for time series analysis, right? But in the end, it has certain components that could be useful for other applications as well. Let's say, assuming that you can make minimal changes to the design, what other applications could be accelerated with this type of accelerator?
So thanks a lot for the question, Juan. And yeah, this is quite a good question. The thing is that NATSA is basically using floating point operations to perform, like, for example, the dot product and the distance calculation. So whatever application that follows a similar sliding window pattern and is based on floating point operations would be a good candidate to be, to be explored and think about what are the modifications that if the application has a similar pattern would be will be, the modification won't be very traumatic, let's say. So these kind of applications will be good candidates.
Okay, makes sense. Thank you, Ivan.
Thank you very much.